So we're talking about solids, specifically crystalline solids. And scientists like to divide things into categories, right? So we can divide crystalline solids into 3 categories based on what are the particles, what are the smallest units. Are they molecules? Well, then it's a molecular solid. Are the individual pieces ions? And it's an ionic solid. Or are the individual pieces, particles, atoms? Then we have an atomic solid. Atomic solids can be broken into 3 more categories. Non-bonding, where the atoms are not bonded to each other, they are just held together by dispersion forces. You have individual atoms. An atom itself cannot be polar, but it can have spontaneous dipoles and dispersion forces, and that's all that's going to hold those together. We can have a metallic atomic solid, where these are metal atoms and they're held together by metallic bonds. Or we can have a network covalent solid, where we've got covalent bonds holding the atoms together. Let's look at each of these individually. So a molecular solid, the individual units are molecules. This is probably the biggest category. Examples would be solid ice, dry ice, any solid molecular compound. The molecules are held together by intermolecular forces. And the strength of those forces is going to depend on whether the molecules are polar or not, and the size of the molecules. But intermolecular forces are fairly weak, and so molecular solids tend to have low to moderately low melting points. Molecular solids can crystallize in different structures, and those are called polymorphs, different shapes. And the different polymorphs can have different melting points, different solubilities, and other properties may be different. So this is important in pharmaceuticals. Different polymorphs can have different physiological activities. It's also important in making chocolate. I don't know about you, but I like chocolate. There are 6 polymorphs of cocoa butter. And they have different melting points, and they have different textures. Their density and stability is also different. And so as you melt chocolate and let it cool down again, exactly how hot you get it and how fast you let it cool down, all of this affects how it solidifies. And that will affect its texture. The desirable form is form 5. It's got a good snap to it, it's smooth and shiny, and it'll melt in your mouth. If you leave chocolate sitting at room temperature for a long period of time, it will gradually change into form 6. Now it's not just firm, it's hard, and it's got some blooming on it. This is bloom. It gets this white stuff. That's not mold, it's not toxic or anything, it's just that the molecules have rearranged, and so this chocolate is not going to taste as good, but it's not bad. It's just not as good as it was. So there's more in the book about that if you're interested. Ionic solids, we've got the composite units being ions, things like table salt, calcium fluoride. Ionic bonds are holding these together. Ionic bonds are very strong, and so these are going to have high melting points, and we'll talk about this in more detail later. Atomic solids. So the units are atoms, not molecules or ions. Examples would be solid xenon, iron, or silicon dioxide. So a non-bonding atomic solid would be something like solid xenon. You just have individual atoms, they're not bonded to each other in any way, just dispersion forces. Very low melting points. And in fact, the only examples of this are the noble gases in their solid form. So kind of a useless category if you ask me. Metallic solids, these are pretty important. This would be any metal element would be a metallic atomic solid. Here we have the metal atoms and a lattice, and they are bonded together by metallic bonds. Remember, we talked about the electron C model, where they've all sent their electrons out to play, and the electrons moving around are what hold the atoms together. Melting points for metals vary. Liquid, mercury is a liquid at room temperature. Gallium will melt in your hand, but other metals require extremely high temperatures to melt. And then network covalent atomic solids. Here we have individual atoms, but they are bonded to each other by covalent bonds. So why aren't these molecules? Because the entire piece of solid is essentially one molecule. It's not discrete molecules held together by intermolecular forces. The atoms are bonded to each other throughout the entire crystal. Examples would be diamond, graphite, and silicon dioxide. The structures here are limited due to the hybridization of the orbitals involved in the bonding. So like with carbon will do an sp3 hybridization, and you're going to have tetrahedrally spaced bonds. That's going to limit the crystal structure. Network covalent atomic solids have very high melting points because covalent bonds are very strong. So we should be able to answer this kind of a question. It's helpful to just not overthink these because they're actually quite straightforward. What type of atomic solid is Au? Metallic. How do we know that? Well, it's a metal. How do we know that? Well, it's in the metal section of the periodic table. Au happens to be gold, but even if you don't recognize or remember that, we can find the symbol on the periodic table, and it's right there in with the metals. Any metal is going to be a metallic solid. Okay? Here's another kind of question. Which solid would you expect to have the highest melting point? So melting point depends on strength of intermolecular forces or bonds that are whatever's holding the things together. So what we need to do is identify what are the particles here and what's holding them together. So in MgO, what are the particles? We have magnesium and oxygen, and these are ions, right? So they're held together by ionic bonds. Are ionic bonds strong? Yeah, they are. I2 solid. What kind of a particle is I2? Is it an atom? It's a diatomic molecule, right? So we've got molecules here. What holds molecules together? Intermolecular forces. Are intermolecular forces strong? They tend to be pretty weak compared to ionic bonds. And then for krypton, what do we've got? Atoms, molecules, or ions? These are atoms. And what holds atoms together? Intermolecular forces again. It's the dispersion force. Because this is a nonpolar molecule, this is also dispersion force. Yeah. That's a good question. Which is stronger, an ionic bond or a covalent bond? You can't answer that with a blanket statement. It depends. Yeah, it's complicated, right?
So if there was a covalent bond in here, because we have the ionic, so if there was like a
Oh, so like if we had a covalent network solid?
Like if it was to be this question on the exam, I asked which one has the highest, or do
So we wouldn't ask you that because you don't have the background information to be able to answer that. Yeah. We don't just ask random questions on these exams. We pick the questions carefully to avoid the ones that you don't have the knowledge to answer. So here, identifying the highest melting point, it should be relatively straightforward. Which is the highest melting point? The one with the ionic bonds, the strongest things holding it together. Here, we can answer the question, which is the lowest. When we look at these two, they both have the same kind of force. What did we learn about the strength of dispersion force? It depends on what? The molecular weight. So if we look at the I2 molecule versus a krypton atom, which one weighs more? The I2 molecule should weigh a lot more. And so then we can predict that the dispersion forces here are stronger. Stronger forces means higher melting point. So we would expect that this one would be in the middle and that this would be the lowest melting point. Because those two are elements, we can also figure that out just by looking at the states on the periodic table. What state is xenon or krypton at room temperature? It's a gas. What state is iodine at room temperature? It's a solid, right? So it has a lower melting point. Any questions? One of the things that correlates strongly to success in science classes, well, actually in STEM courses in general, is it could be described as grit, determination, a willingness to tackle something, right? Some people have this naturally and other people need to develop it. But we can all get more grit and just being determined, I'm going to solve this, instead of just throwing our hands up when the answer doesn't come immediately. Let's pull it apart. Let's think about it. What can I write down that I know about this? How can I possibly even just eliminate some of the choices this way? And that's a skill that you can practice, and it'll benefit you in all aspects of your life.